In this video, we are going to address some of the topics in geometry, similarity, and right triangle standard number 4. You ought to recall that standard 4 were about those proofs. Specifically, we have a couple of proofs regarding similarity that we need to take a look at. Now, our primary focus for today's work is to prove the theorems. We're not going through and using them yet. That will be in a future topic with some of our later homework. The focus today is simply to prove the Triangle Proportionality Theorem and also to prove the converse of the Triangle Proportionality Theorem. Now, in the video, one of the things that is going to be missing, I'm also working on the marker board. And so over here on the marker board, I'm going to put down an example using numbers. But on the smartboard itself and in the video, we're going to prove it algebraically. We're also not looking at a 100% rigorous proof. We're looking at some of the main ideas. And so start by copying down this problem. If you're doing the video, pause at home. Now, before we look at proving it, I'd like to help us understand a little bit what's going on with this particular thing. We have seen before, based on similar triangles, that if we wanted to, we can use similar triangles to create proportions. For instance, taking left paired with left, we were able to create a proportion of AD compared with AB, left side compared with left side, matching that with right side with the right side, and so we have also been able to create proportions like this. In terms of pieces on the marker board, consider what I have drawn, and in the video I'm going to pause it now. Although we have taken proportions that looked left matching left, right matching right, this particular theorem tells us, suppose we have this picture. If we have this picture, then we could set it up, and I'm just going to put up some different numbers now. 10, 30, 12, and 36. If we had numbers like this, instead of setting it up as 10 and 40, 12 and 48, we can instead set it up 10, 30, 12, 36. So basically it's top left and top right, bottom left and bottom right, and they go exactly in the same position that we would have in the proportion. This is what the theorem will do for us. It gives us a shortcut, giving us more correct ways to set up a proportion. We are trying to explain why. Now, to help make some of the algebra a little bit easier, our first step is going to define a whole bunch of stuff. All right, so define AD, we're going to call the letter A. AB, we'll call the letter B. AE, we'll call C. And I need to change that to an equal sign. EC, we're going to call the letter D. Angle ADE, we're going to call angle 1. Angle ABC, we're calling angle 2. Angle AED, we're calling angle 3. And angle ACB, we're calling angle 4. Write them down. Basically, what this will do for us, this is A, this is B, this is C, D, angle 1, angle 2, angle 3, and angle 4. We're starting off just by changing some of the notation so it's a little bit easier to work through. As we know, how do we always start every single proof? By starting with the given. And our given here, we have DE parallel to BC. Now, before we go any further, I would like to map out the big ideas of the proof. The main ideas for this particular proof, we're starting with the given that we have parallel. Those parallel lines will tell us corresponding angles are congruent. Having two pairs of congruent angles, angle will tell us the top triangle is similar to the overall big triangle. Triangle similarity will allow us to create a proportion, but not the right proportion. After that, we're going to use some algebraic manipulation, just moving some pieces around until we get this proportion over here that we want. So, writing out the general outline in symbolic notation, parallel lines are going to give us corresponding angles are congruent, which is going to give us similar triangles using angle. That will give us a proportion, and using algebra to move some things around, we get this proportion that we actually want. This is the main idea behind the proof. All our sequence of steps put down in one line. To write up some of the details, though, it'll probably take us 10 or 11 steps. So let's really get into it now. Well, first things first. We have already said we have parallel lines. Because we have those parallel lines, angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. Why? Well, because parallel lines give us corresponding angles are congruent. Knowing that we have those two pairs then, angle and angle, as I just mentioned, having two pairs of angles sets up angle similarity, telling us that triangle ADE is similar to triangle ABC. Now that we have those similar triangles, we can create a proportion. And I would like to point out over here in the markers, showing the numbers, how to set it up. Do you remember me mentioning that there are 6 different correct proportions that we can set up? Well, given that we have a lot of correct proportions to set up, there are many different correct ways that we could continue the proof. The one that I am choosing is designed specifically to give us the easiest algebra after the fact. If you wanted to pick a different proportion, it would work. It's just more lines, more steps, more work. I'm picking the one that I think is the easiest. And so the proportion I'm creating is left paired with left. How big is the entire left-hand side? All right, so as we just noted based on the markers, our entire left-hand side, top plus bottom, gives me the whole left, A plus B. That's the whole left side. Creating our scale factor with just the left side of the top part, that gives us A plus B. And come on, fix my colors here, board. A plus B all over A. That's our scale factor. do the same thing on the right-hand side. What's the entire length for the right-hand side? How long is the left, the right? We're not using the numbers. We know with the numbers that I have on the board, it's 48. But we're not in the proof. We can't use actual numbers. We have to do it with variables. So using variables, what's the entire right-hand side? AC is the part for the whole thing. You're absolutely correct. But we're not writing it up that way. We're trying to use these lowercase letters. Thank you, Moses. The entire right-hand side is C plus D. And you also correctly identified that we will put that over just C. This proportion we get by the definition of similar triangles. The definition of similar triangles says we can create these scale factors and the scale factors will be equal. Well, when we got around to solving proportions with our earlier work, what did you do to solve a proportion? What would you do? Yes, we would have to cross multiply these pieces. So if we cross multiplied, we'd have C times A plus B. And the other one, we'd have A times C plus D. So that's our next step. When we cross multiply, we will get C times A plus B and A times C plus D. As we saw on the marker board, our next stage is to multiply across with the distributive property. And based on distribution, and admittedly I'm being a little bit sloppy with writing letters down perfectly as the distributive property would require, we'd have A times C plus B times C equals AC plus AD. We're going back to our marker board. You notice how both sides of the equation have that 120? Or in this instance, both sides have AC. We can subtract that off. If we subtracted AC from both sides, what do we wind up getting? Well, what happens if we were to subtract off AC and subtract off AC? Those things cancel, and what are we left with? BC equals AD. That's the next line that we will write out. All right? Now, I would like to go back up to the top and remind you what we're trying to get. The thing we are trying to prove, DB is B, AD is A, EC equals C, and AE, I'm sorry, that's D and C. You notice how with the proportion we're trying to create that we have B on top by itself? And we also have D on top by itself. That's what we need to get with our proportion here, with this equation. So what would we have to do to get the B by itself? That is to get rid of the C. What would you have to do to get rid of times C? We'll have to divide by C. Now we also wanted D to be in the numerator by itself. So how do we get rid of the times A? We'll have to divide by A. this is actually going to be our next stage. What we will have, if we divide both sides by AC, as I had just written, we see that we wind up with BC over AC equals AD over BC, or AC. And at this stage, we can reduce fractions. If we simplify those fractions, what winds up canceling? C over C would cancel. A over A cancels. And what are we left with? We're left with the proportion B over A equals D over C. But we're noting, of course, that is exactly what we wanted back up at the beginning. Well, now we'll just change our variables right back and then we're finished. So that's D, and this thing is C to fix that. So using substitution, we wind up with, and I've forgotten what the letters were, dB over AD equals EC over AE. And we are completely finished. Now at this particular stage, we've done the proof. I would like to show you a little bit on some of the things that we're going to wind up doing with this. Now, this particular one, it's not the primary focus, but consider we have a triangle. And we can have a segment drawn. It does not have to be the mid segment, so it does not need to be in the middle. But let's say we know that these things are parallel, so we get this picture. Let's say what this thing does for us, this is a type of problem that we've already been able to solve. If we knew that we had similarity and the parallel lines would have told us they're similar, up until now, when we wanted to set up a proportion, we've had to take it left side matching left side. And that would have given us the proportion right side matching the entire right side, which is 4 plus x. We know that we could cross multiply. We know that we could combine our like terms. We could solve that proportion. We already have the ability to do this. Where the Triangle Proportionality Theorem is helpful is it gives us a shortcut so that instead of needing to set up this proportion in the purple, we could have simply said top left, bottom left. Top right, bottom right. And you tell me which proportion looks like it's easier to solve. That's why we care about this. We already have the ability to do it without this theorem, but this theorem just gives us something that's easier. Now, there are some things that we have to be careful about with this. In our future video, we will discuss some of the risks with this particular thing. In particular, there is one really common mistake that students tend to screw up on a lot. I will caution you against it in our video based specifically on how to use this thing. Right now, we're focusing just on the proofs. So let's continue further and say, let's now prove the converse. Remember, the converse is working backwards. The original theorem said, start with parallel lines and then show me that the proportion is true. We're not doing it that way now. We're not starting with parallel. Instead, we will start with the proportion. Working backwards, we will show that the lines had to be parallel. Now there are a little bit of a risks to this. In particular, earlier we used the fact that parallel gave us corresponding angles are congruent, and that's how we created the similarity before, based on angle. Well, we don't have that now. We will need a different method of showing similar triangles. And the idea that we will have this proportion that we're starting off with, we are going to use some algebra and manipulate it until we can get to the point that we would have AB over AD, so left matching left and right matching right. With some algebraic manipulation, we're going to work backwards to create this proportion. Well, this piece is telling us that we have two pairs of sides that are similar, because they would have the same scale factor. We'll also observe that both triangles, they share this angle A. As a shared angle, we know it's congruent to itself. So with a congruent pair of included angles, we're actually setting up side angle side similarity. So this proportion is going to set up side angle side similarity, giving us similar triangles. Once we have those similar triangles, well, the definition of similar triangles tells us that your corresponding angles are congruent. The matching angles will be the same. But we also observed in an earlier unit that corresponding angles being congruent forces these lines to be parallel. Very similar in idea, working backwards, but there are a couple things that we're going to have to be careful about. And so we're going to start off with the exact same stuff. And I'm not going to write it up, but we're going to start off with the same thing. We're letting AD be equal to A, and letting the next piece and the next piece, all those same things that we had before, they're absolutely identical. So you can copy them off of your notes, or if you prefer, we're using step number 1, exact same thing again. Pause the video to write them down. All right, so to continue now, we'll of course start with the given. We have AD equal to DB, I'm sorry, AD over DB equals AE over EC, and that was given. Just like last time, we want to make this algebraic substitution so that we have some easier numbers to work with. Remember, AD is just A. Hang on, do I have this written down correctly? AD is A, DB is just B, AE is C, and EC is equal to D. We're just substituting in those variables as we defined. Well, what's our standard thing now? Whenever we see a proportion, what do we typically do with it? Exactly. We'll cross multiply. So when we cross multiply these, what do we get? AD equals BC. Now remember, we're trying to work our way backwards through this thing. And so when we go back to the first one, we'll note we had a stage down here where we said AD is equal to BC. We have that. What did we do before this? But if we're going to distribute, we have to have some addition and subtraction. So basically, to create this line, we had to subtract AC from both sides. Well, how do you work backwards from subtraction? We'll add. So coming to this one now, instead of subtracting AC, we'll add AC to both sides, which will give us AC plus AD equals AC plus BC. Now, of course, we will also note the step we did before subtraction was distribution. So how do we undo the distribution? Or rather, we used distribution before to get rid of parentheses. So our task then has to be working backwards. Instead of getting rid of parentheses, we have to make them. Well, the distributive property is also used to make those parentheses or to change the order of operations, to rewrite it into an equivalent expression. In this instance, what do the first two pieces have in common?
The A.
So we'll factor out the A and see what gets left behind. C plus D. From there, on the right-hand side, what do they have in common? So we'll factor out the C and leave behind A plus B. Well, remember how this whole thing began? The proportion we had in the very, very beginning was A over B and C over D for the numerators. I'm looking here at line 5. Well, once again, we want to get A plus B by itself. We want to get C plus D by itself. And so how do we get them by themselves? We will have to divide by C, knowing that the C's are going to wind up canceling. On the left-hand side, we will also have to divide by the A to make certain that the A's cancel. Now, unfortunately, we can't just divide each piece by itself. We'll have to divide both sides by the A, because we need to get rid of the A on the left. And we'll have to divide both sides by C to get rid of the C on the right. And so we wind up with this proportion. From this stage, we can reduce or simplify those fractions. What cancels? C will cancel with C, A will cancel with A, and we are left with the proportions C plus D over C equals A plus B over A, which is, of course, the exact same proportions that we began with back in the beginning. These are the two things. This is telling us a scale factor equals a scale factor. These are the two things that are setting up the side and the side for side-angle side similarity. The piece that we're missing now is the angle. So let's write that in. We would have angle ADE is congruent to, I have the letters in the wrong order there. DAE is congruent to angle BAC. And once again, I'm looking at this angle up the top. DAE with BAC and that's because it's a shared angle. Remember, the more formal name for that is the reflexive property of congruence. But we're being informal with this description. So together, these two lines, 8 and 9, 8 and 9 come together, and those are the things that are setting up side-angle-side similarity. Because of side-angle-side similarity, we know that triangle DAE is similar to triangle BAC. And we're almost done now. Because the triangles are similar, we know that matching angles are congruent. Well, going back to what we had in the beginning, our picture gave us angle 1 and angle 2 are corresponding parts of the same triangle. So we have angle 1 is congruent to angle 2. And that stems from the definition of similar triangles. Of course, though, DC. Because corresponding angles are congruent, we've mentioned before that corresponding angles being congruent forces lines to be parallel. And we're done. Definitely a lot of work. But this whole process is used to say, if we have this type of a picture, and we can actually show the proportion works. So for instance, if we have the picture, and we can show basically, I'm asking, are these lines parallel? Yes or no? This theorem lets us say, set up the proportion. Is it true? 360 and 360. So yes, because the proportion is true, we are certain these lines definitely are parallel. That's what the converse is used for. Are the lines parallel, yes or no? This just gives us another way to figure out if they're parallel. And as I mentioned before, we will have a homework assignment. We will have more in-class work practicing these skills, practicing how to use these. This particular video is just what are the steps in their proof. So we're using this stuff to address standard number 4, the proofs. Our homework and the word problems will address standard number 5, where we actually use the theorems.